Hello friends, in this video I'd like to solve the following problem from the Spanish Mathematical Olympiad, final round 1979, problem number 3. So we wish to prove that the following sum, n choose 0 plus n choose 1 squared plus and so on plus n choose n squared equals 2n choose n for every non-negative integer n. So my hint for this problem, the simplest and fastest way to solve it, to show that it is true, is by using so-called Vandermonde's identity, Vandermonde's convolution, which says in general that sum from k equals 0 to n of R choose k times S choose n minus k is R plus S or choose n. So upper indices are added and lower indices somehow are added as well. And this entire sum disappears. Knowing that formula makes the previous problem almost trivial. Or the other way is by induction. Never failing induction. I recommend using this formula. So give it a try and see you in a moment. Okay, so maybe I will not erase this identity and let's just apply it. In our case, not directly, but let's write our sum from k equals 0 to n choose k squared. Now, by well-known property of binomial coefficient, n choose k is exactly the same as n choose n minus k, because choosing k things from n elements is exactly the same as choosing the rest of elements, the elements which are not chosen. Does it make sense? So, for example, let's say that we have a group of 10 people and we want to form a delegation consisting of 2 people. So we can do it in 10 choose 2 ways, but it's exactly the same as choosing 8 people which will not be in the delegation. 10 choose 8. And now, by the Vandermonde's identity, this sum is exactly of the form above, and it's n plus n choose n. So it's 2n choose n. And that concludes our proof. But let's spend a little while thinking about why Vandermonde's identity is true in the first place. Well, it's possible to prove it by induction, but there is a better way to think in terms of combinatorics. Because let's look once again at Vandermonde's identity. Let's look first at the right-hand side. On the right-hand side, we have R plus S choose n. So the right-hand side is the number of ways to choose n things from a collection of R plus S terms, R plus S elements. So let's say that we have, it's an example which will illustrate. So let's say that we have R plus S elements, and we group them in 2 groups. In one group, let's say that, here we have R elements, and the other group will consist of S elements. And we wish to, let's say, choose 3 elements. Well, one way to do it is just to to choose to add r plus s and then choose n elements, but the other way to do it is to consider all possibilities, because there are what possibilities? One possibility is to choose 0 elements from the left group and to choose n elements from the right group. So it's one way to choose n elements. The other way is to choose, for example, one element from the left set and to choose the remaining n minus 1 elements from the right set, and so on. For example, the next term will be choosing 2 elements from the left group and choosing n minus 2 elements from the right group, and so on, up to choosing everything from the left group and nothing from the right group. And we see it should be visible that we cover every possible way of choosing n things from a collection of r plus s things. And so it's combinatorically, it should be and is in fact exactly the same as r plus s or choose n in the first place. So I hope that it was somewhat clear for you. If not, you can always convince yourself that Vandermonde's identity is true by using mathematical induction. But it's boring, so I won't do it. So, thank you for watching and see you next time. Bye.